Okay, we are back to our next recording here. Okay. So let's go to our next lab, which is going to be the, not this one, the spectral sequence and the HR diagram. So that's our next lab is going to be lab 11. The spectral sequence and the HR diagram, we're going to do a lot of good stuff here. We're kind of moving into the astronomy about the stars now, about stars and their what kind of information we can glean about them from studying their spectral types. So introduction. The Hertzsprung-Russell diagram, or HR, displays the luminosity versus surface temperature for individual stars on a graph. A star of a given mass will follow a specific path on this graph as it ages. So basically, this is a plot of the main things that are being plotted on the HR diagram are the luminosity of the star on the vertical scale. That means how bright it is. And then on the horizontal scale, it's the surface temperatures being graphed. So we would expect that for most stars, low temperature stars will have low luminosity and high temperature stars will have high luminosity. So that makes sense. So when stars are living on this main sequence, when stars are still alive, they are what's known as the main sequence star. This makes the diagram a crucial tool for understanding stellar structure and evolution. This lab introduces the tools astronomers use to identify stars of a main sequence and how that information is used to estimate the distance to the stars and the age of a star cluster. So we want to be able to read information from an HR diagram, calculate the distance to a star based upon the distance modulus, and estimate the age of a cluster based upon the turn-off point for stars. That's all. Those are the goals. So we got the HR diagram. So the horizontal axis of the HR diagram uses the BV color index, a measure of a star's surface temperature. So that's the blue-violet index, and that's a measure of the star's temperature. So hot stars will appear more blue, and then cold stars will appear more red. So that's kind of the idea of the color index of the star. Since spectral class and color index are primary measures of the surface temperature of stars, we may use any of these three quantities to specify the color on the horizontal axis of the HR diagram. The color of the star is related to its surface temperature according to Wien's displacement law. So if you remember in an earlier lab, we did the Wien's displacement law. The wavelength at which a star emits most of its light is inversely proportional to the surface temperature of the star. The spectral class of a star is its position within the Harvard Spectral Classification System, OBAFGKM. Oftentimes we use this mnemonic to remember this. Oh, be a fine girl and kiss me. Oh, be a fine girl and kiss me. That's that's the mnemonic used to remember this Harvard Spectral Classification System. The color index is a numerical measure of the main color of light emitted by the star. It is defined by taking the difference in the magnitudes of the star at two different wavelengths. So it is defined by taking the difference in the magnitudes of the star at two different wavelengths. These magnitudes are determined by collecting the light of a star through filters, which allow a limited range of wavelengths of light to pass through. So that's why it's called the BV color index, because you use a blue filter and a violet filter, and then you determine how bright that star appears. So three standard filters used for color indexing are ultraviolet, blue, and V. V stands for visual. So Blue is the, I guess it filters out anything but the blue, and then visual filters out any wavelength but the visual. So a blue filter only transmits blue light, you see. White, a visual filter only transmits yellow light. Oh, sorry, I meant not white. So it says a blue filter only transmits blue light, while a visual filter only transmits yellow light. Oh, I see. So you see the V, which is stand for visual, is only allowing the yellow because the yellow is sort of in the middle of the visible spectrum, from red, orange to all the way to blue. So yellow is in the middle of that range. So the visual filter only allows the yellow to go through. So exercises in this lab will use the blue blue visual color index for the horizontal exercise for the horizontal axis of the HR diagram. So if we wanted to see, for example, examples of HR diagram, you could take a look at so many different examples and images online. You see, so you can see this one, for example. This one uses the luminosity of the stars. So you see on the vertical scale, you see the 10 to the 6th on the top. Those are the most luminous stars and the heavy mass stars. And down at the bottom are the low mass stars. And then on the horizontal scale, the temperature is hot on the left side, 40,000 Kelvin. And on the right side is 2,500 Kelvin. So that's one version of the HR diagram. This other version is it's still the hot ones are on the left and the dim ones are on the right, but the hot ones are the O classification scheme. O, be a fine girl and kiss me, and the M is the low temperature. And on the left side, instead of graphing the luminosity, let's take a look at this one. This one is a good example. You see on this one, you see how on the left side here, it goes from -10 on the top all the way to 15. So basically they're graphing the luminosity, absolute luminosity of the star, known as capital M. So the more negative the absolute luminosity, the brighter the star is. So -10 stars are the brightest stars on the top. And then positive 15 stars are the stars on the most dimmest, you see. On the right vertical axis is the regular luminosity of the star, with 1 being the luminosity of the sun, and then 10 to the second being 100, and then 10 to the fourth being the highest luminosity. And then on the top are the temperatures. 25,000 Kelvin, 10,000 Kelvin, 6,000. So do you notice as you move to the right, you get the colder stars all the way down to 3,000 Kelvin. And then on the bottom is the spectral type. Oh, be a fine girl and kiss me. So you can kind of see all 4 things being plotted here on the graph. And then this is a colored version of it. Very nicely done. Red stars on the right are the cold ones, then orange, then yellow. And then you got the main sequence stars are the ones that are still living. And then the giant stars, and then the supergiant stars. And then the white dwarfs are the stars that are dead, which our sun will end up as a white dwarf star when it dies. Okay, so that's a good example of one. And then there's different versions. Let's see here. I'm trying to find one with the color index showing. Let's see here. This one has the spectral types on the bottom and the temperatures on the top. Let's see here. Is there one with a color index showing? Well, no, it's this still the spectral type. So let me actually Google examples of HR diagram with BV color index. Let's see if we find one. There it is. There it is. You see here? You see how on the bottom now you got the spectral type showing O, B, fine, girl, and kiss me. So those are spectral, known as the Harvard Spectral Classification System. Now the BB index is shown right above it. You see, a 2.0, it's shown in blue. A 2.0 are the red-looking stars. A 0.9 are starting to get less and less red, transitioning into a yellow, orange, and then a yellow. Notice our sun is in the yellow range, yellow-orange range. So 0.6 is about yellow-orange, and then a 0.3 is a white-bluish-looking star. And then a 0.0 is the more like starting to transition to white and blue. And then negative 0.5 is on the most left side, is the bluish color star. So you see those are the color index, BB index, that are showing. Yeah, very nice. And then the temperature showing on the top. The absolute magnitude is showing on the left vertical axis, and on the right side is showing the luminosity of the stars. Okay, so that's kind of what we're talking about. The HR diagram has a lot of information on it. Okay, so exercise. Okay, so this big M is what's known as the star's absolute luminosity, the one we were just talking about. The sun's absolute luminosity is a 4.5. You see, 4.5. So look here at where the sun would go. You see where our sun is on this chart? Let me zoom in on the sun. Zoom in on the sun right here. Now go to the left from where the sun is, all the way to the left, 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 left. Where does that take you? You see, so if you draw a straight line all the way to the left, notice that it's 4 point something. It's between a 4 and a 6, you see? So you go like that, straight line, straight line, straight line, and it's actually almost a 5. So on the absolute magnitude scale, it's almost a 5. And if you go to the right, by definition, the luminosity of the sun is a 1, because we compare the luminosity of other stars to the sun. So by definition, it is a 1, you see? So now, for example, Altair would be, if you go straight across, would be 10 times brighter than the sun. You see, Altair would be around 10 times brighter than the sun. And then if I go to the left on the luminosity scale, it would be like a 2.5, you see, 2.5. And then you go to the right, that's a 10. Now, if I go, let's say, RR Lyra right there, or maybe Aldebaran, let's go Aldebaran. If you go to the right, it's almost 100 times brighter, not quite. So almost 100 times brighter. Now, if we go to the left, it's almost a 0, you see, on that scale. So one of the things we're going to learn is that for every unit of 5 on the absolute magnitude scale, the luminosity of the star increases by 100-fold. So if the sun is a 5, for example, if the sun is a 5, we would expect that a star that is rated as like a Regulus is rated as a 0 almost, or Aldebaran is rated as a 0. So we would expect that star to be 100-fold brighter than the sun, approximately. And if you go to the right, You see, it is 100-fold brighter. There you go. So then, so you see, so the sun is a 4.5, L goal is a negative 0.2, and Sirius is 1.4, Achernar is negative 2.7. Now, the little m is how bright the star appears to us. How bright the star appears to us. That's known as the visual magnitude. So we would expect the sun to be the most brightest looking star, so it gets the most negative number, negative 26. Algol is not as bright looking. Sirius is the brightest looking star in the sky, so it gets a negative 1.5. And then Achernar gets a 0.5. So the apparent brightness depends on not only how bright the star actually is, but how far away the star is from us, you see. So the apparent brightness and the absolute brightness are connected, but the apparent brightness depends on also its distance from us. So here it says, from the information in the above table, sort the stars by actual brightness. So you put this here, take a picture of that, of your result, and then question 2. From the information above table, sort the stars by apparent brightness, from most apparently bright to the least apparently bright. So most apparently bright should be the one that gets the most negative m, the most negative little m, right? So that should be the sun. And then you go to then the next negative. Okay, so remember with the brightness, if you've taken this in astronomy lecture, that on the brightness scale, the thing that has the most negative is always considered the brightest, or it appears the brightest, right? And then the more positive, the least brighter it appears. I always tell people the analogy with the game of golf. The more negative is your score, the better player you are. So if you're, for example, if you're Tiger Woods at the height of his career, he could score easily negative 15, and that we would say, wow, that's amazing. In other words, on a course that's a 72 par, he would score 57, which means he got all 18 holes in 57 hits, which is amazing, because a good player should get 18 holes in 72 hits. So then we would say his negative 15. It took him 15 less hits to get to finish 18 courses of golf. 18 holes, I meant 18 holes of a golf game. So if you're 0 par, that's you're still pretty good. But more negative you are, the better golf player you are. You see, so that's kind of how this magnitude scale works. Okay, so for that one, you take 2 pictures and your results. And I think that's it for that. So then exit this out. Distance modulus. So by matching an HR diagram of a star cluster, which uses apparent magnitudes, to standard HR diagram, which uses absolute magnitudes, okay, the distance modulus and thus the distance to the cluster can be found. Pictured here is the Hyades star cluster. If photometric measurements of the magnitude of each star through U, V, and B light filters were made of all the resolvable stars in the star cluster. So you see what they're doing is they're measuring how bright the stars look in that star cluster through U, V, and B light filters. The stars could be plotted according to their measured apparent magnitude and color index. Could these stars form a regular pattern similar to the standard HR diagram? A standard HR diagram is a diagram in which stars are plotted by absolute magnitude rather than apparent magnitude. The Hyades open cluster. So here's an open cluster of stars. So you can see here, this is probably the brightest one right here. That's the star of the Hyades. There's another good bright star, orange looking. Those are the coldest. Remember, the red, orange looking stars are colder. This is orange looking right here, right there. Now this one here is blue looking, so it's going to be hotter, right? Blue looking and it's hotter right here. Oh, this is even better to view them like this. Oh, that's much better. Oh, wow. Oh my God, it's spectacular. I know what a difference when you click on it. Wow, beautiful picture. You could tell this one is more blue looking right here, and that's more red looking. And then, so what you could do is then just take all of these stars, see what color they dominate in. From there, ascertain their color index and their temperatures and their spectral types. And then you determine how bright they appear to us. And then from there, we can ascertain their distance to that cluster. So now we know that if you click here, you get a much better image of these things. So if such a pattern were found, the apparent magnitude of the star cluster's stars could be calibrated to an absolute magnitude by observing where the cluster's plot fits on the standard HR diagram. From this, the distance to the cluster could be determined. Now, here's why a star cluster is so unique, because the distance to the individual stars of the star cluster should be about the same from us, because that cluster should be close together. So if the distance to one of the stars is, let's say, 102 million light years, then we would expect the distance to the other stars to be around 102 million light years. So within maybe 100 or 105. So we would expect them to be close to each other, relatively close, depending on the size of that cluster. So here it says, let's see, what's the, let's see, let's minimize this. No, it's okay. I think it was good. The Hyades cluster exercise allows you to find out the apparent and absolute magnitude and the distance modulus for the Hyades cluster. Look first at the grayscale picture of the central region of the Hyades cluster. Okay. Several of the stars in the picture have been highlighted in yellow. When you click on the star, its apparent magnitude M and color index BV will be displayed in the windows below the pictures. Oh, okay. Use this information to decide where the star belongs on the adjacent blank HR graph. Drag the star over to its appropriate place on the graph. Crosshairs will appear to help you. If you drop the star in the correct location, the star will stick. Otherwise, it will appear back in the star cluster picture. And you must try again. You must plot all the highlighted stars to go on to the next part of the exercise. So let's say you click here. Oh, you see the apparent luminosity. Not sorry, they don't give you the apparent luminosity. They give you the absolute. Wait, is it absolute or the? It looks like it's capital M. When you click on its apparent magnitude, big M. 0 to positive 25. You know what? They wrote it, they miswrote it. They should have wrote that little m, because this is the apparent luminosity. Hold on there. This is the apparent luminosity. They should have written little m. See, it got me confused too. They should have wrote this the apparent luminosity with the little m, not a capital M. So what they're giving us is the apparent luminosity of the star, 9.52, and the color is 0.93. Now drag it over here. Apparent luminosity is 9.52, so that means it's right here. And you know what? Let me magnify it a bit. So let's go like this. Any of these. So apparent luminosity 5.72, color index 0.32. So 0.32 is going to be somewhere here. And then the magnification, I mean, sorry, the apparent luminosity 5.72. So the smaller that number, the apparent luminosity, that means the brighter it appears. 5.72 is an okay bright looking star, but you need a telescope to be able to see it. So then let's go up all the way to, oops. So, oops. Did it snap into place? Hold on. I guess it did. Yeah, it wouldn't have snapped into place if it was so 0.32 and it was a 6. So now let's see, here's this one. 1.63, that's a more red looking star. So notice that this is actually showing you their position in the sky, not their position on the HR diagram. So just because a star is on the right lower side doesn't mean its HR should be down here, you know? So this is just showing you its position in the sky. So then you click on it, 14.68, 1.63. 14.68, 1.63, 1.63, 14.68. Somewhere here, right? Oh, okay, it snapped into place. So if it's snapping into place, because these numbers are, this big circle is so big, it's kind of snapping into place as long as you have it roughly in the right place, you know. So what you could do for this one is take snapshots of, let's say, 5 of the stars, like when you click on them, and then you have them in the correct position, like this. So let's say I have it in the correct position before it's going to snap into place. And then the left side should be showing you, the bottom should be showing you the BV and the 9.11. So you're kind of showing how the process was done by you putting it in the right place. How did you put it in the right place? So 0.87 would be here. 9.11 would be here. 9.11 would be here. Then take a snapshot of that right there. And then just go click, you see, but then that disappears. So take a picture of it right before it disappears. And do that to all, no, do that to 5 of them. And then take once you do the final of all of them, just take a snapshot of just the graph showing that you've placed all of these onto there. Okay, so like, for example, you could show 4 of these, 4 random ones, and then the very last one that you're about to place there, that could be your 5th one, you know, and then that you could show exactly that that was your very last one, and then what its M and BV were. So 4 random ones, and then the very last one. Okay, then here, Heidi's cluster exercise. So follow the instructions on the Hyades cluster exercise above to plot the photometric data of stars in the Hyades cluster and determine the distance modulus for the Hyades cluster. Remember, D equals 10. Wait, did we? Did they already? Did I skip something? Oh, okay. You know what? Hold on. I think I've skipped. I don't know why it went, skipped the distance modulus. Oh, okay. I think before that exercise, it skipped the first page because I was like, wait, they never talked about the formula, you know. So let's go through this. The distance between the apparent magnitude and the absolute magnitude is called the distance modulus, and it can be used to calculate how far away a star is in parsecs. The absolute magnitude, big M, and the apparent magnitude, little m. See, that's what I was saying about apparent magnitude. They should have written apparent magnitude with a little m. are related by the logarithmic equation. Big M is equal to little m minus 5 log d over 10, where the distance d is given in units of parsecs. The equation can be rewritten to calculate the distance as follows. D is equal to 10 to the power m minus big M plus 5 over small 5. The quantity m, little m minus big M is called the distance modulus, since it is a measurement of how distant the star is. In the previous equation, the distance to a star can be calculated from its absolute and apparent magnitude. For example, Omicron Leonis, a star in the constellation of Leo, has an apparent magnitude equal to 3.53 and an absolute magnitude, big M, equal to 0.43. The distance modulus m minus m is equal to 3.10. Okay, so notice here they're giving you the apparent magnitude 3.53 and an absolute magnitude of 0.43. Distance modulus m minus m. So they're doing 3.53 minus 0.43 and they're getting 3.10. Applying the distance formula, we find that the distance to Omicron Leonis is 41.7 parsecs. Okay, so let me show you here how they're doing that. So the little m, let me take a picture of this. The little m was 3.53, I think 3.53, and absolute luminosity on the luminosity scale is 0.43. The distance modulus m minus big M is going to be 3.43. Sorry, this minus this is going to be 3.10. 3.10. So now the distance to that star is going to be what? 10 to the power m minus big M plus 5 over 5. So what's that going to be now? 10. So m minus m is 3.1 plus 5 over 5. And what is that equal to? 10 to the power 3.6 over 5. And that will give you the answer in parsecs. So let's do that on the calculator. So 10 to the power 3.6 divided by 5. 5.25 parsecs away. Is that the answer they got? Let's see here. 41.7 parsecs is equal to 5 over 5. 10 to the power, no, something went wrong, hold on. 10 to the power m minus m plus 5, they're saying they got 41.7 parsecs. So m minus m is 3.1 plus, hold on. I did it wrong. It's it's 3.3, m minus m is 3.1 plus 5 over 5. So then that's going to be 10 to the 3.6 over 5. Did I put it wrong into the calculator? Let's see. 10 to the power 3.6 divided by 5. 4.24. That's weird. 10 to the power 3.6 divided by 5. 5.25 parsecs. M minus M. I wonder if they're wrong. For example, Omicron Leonis, a star in the constellation Leo, has an apparent magnitude M equal to 3.53. M minus M is going to be 3.10. Applying the distance formula, we find that distance to Omicron Leonis is 41.7 parsecs. 10 to the power, so 3.10 plus 5. Okay. I did the math wrong. Wait, hold on. I think it's too late in the night. I'm too tired. 3.10 plus 5 is going to be 8.10. What am I doing? I did 3.10 plus 0.5. I think it's too late in the night. Oh my gosh. Yeah, I see that? A little math mistake. There you go. Okay, so plus 5. So that should be 8.10. Yeah, there you go. 8.1 over 5. Okay, there you go. So 10 to the 8.1. So 10 to the power 8.1. No, 8.1 divided by 5. Yep, 41.6 parsecs away. Okay. Now we could try any other star that we want. See if our just take, for example, any star in the sky. Star Betelgeuse. One of my favorite stars. I usually just go straight to Wikipedia, and it's got all the information that you need, what constellation the star is in, and all the data about the star. You see, it's got the constellation, the right ascension, the declination. It's got the spectral type. See, that's what we talked about a minute ago with the OBAFKM. Apparent magnitude, that's the little m. You see, that's the little m right there. Apparent magnitude J and apparent magnitude K. Oh my God, now that's confusing. There's different apparent magnitudes. This is other than apparent magnitude. There's different apparent magnitude. So then the BV color index is 1.85. You see, then there's the ultraviolet blue color index. That's different. We're using the blue yellow. See, remember visible, V stands for visible, which is yellow. So they're using a blue, visible a filter and then a blue filter to determine its color. Then there's an ultraviolet blue filter, and that's a different scale. And then the distance to the star, the absolute magnitude, oh, that's the one, negative 5.85. So that means the Betelgeuse is actually a really bright star. On absolute magnitude, it's 5.85. Remember, the sun is a 4.8 something. Sun is a 4.8. The more negative you are, the brighter that star is, right? 5.85, and its apparent magnitude is, I believe this is the one. that we should use. Hold on. Apparent magnitude V. Why is there three of them? Explain that is visible to the human eye. Electromagnetic radiation is called visible light or typical human eye. Okay, apparent magnitude J. The J band refers to an atmospheric transmission window centered on. Oh, okay. I don't think that's the one I think ours, the one that we're using is the apparent magnitude V. Apparent magnitude is a measure of the brightness. An object's apparent magnitude depends on its intrinsic luminosity, its distance from Earth, and any extinction of the object's light caused by the interstellar dust along the line of sight. I believe the one we're using for apparent luminosity is this one, the 0.5. The one, in other words, how bright does that star appear in the visible spectrum? That's the one that we're using. Apparent, that's the one they call little m. So now, if we wanted to use that, apparent is 0.5. And then the absolute is negative 5.85. So then what would our calculation be for Betelgeuse? It would be 10 to the power. The apparent would be the 0.5. That's our little m would be the 0.5. Minus the absolute, which would be negative 5.85 plus 5 over 5. Ten to the power, and then this one gets added. So then what would that be? 5 plus 5 is, that's going to be 10.85 plus 0.5, that'd be 0.5, that's going to be 11.35. 11.35 divided by 5. So 10 to the power 11.35 over 5. So 10 to the power 11.35 divided by 10 to the power 11.35 divided by 5. 186.2 parsecs away, we would expect Betelgeuse to be. 186.2 parsecs away. 186.2 parsecs away. And then remember from the first lab that 1 parsec is 3.26 light years. So we could always multiply this by 3 1/4, and we would get the distance to that star in light years. So now let's compare that to the answer on Wikipedia. 186, is that what we should get for Betelgeuse? So what is the distance to that star? Okay, 168.1 parsecs, it's saying. We're close. We're close. Yeah, 168 parsecs. Maybe I didn't do the math right because it's late at night, right? Never work very late in the evenings, guys. Never. Your brain doesn't function well. Okay, so that's kind of the idea. So the thing interesting about this equation is that it's meant to be so that if the little m and the big M are the same on this scale, that it's meant to be the distance to that star. So let me give you a little bit where the idea behind this equation is. If the apparent luminosity and the actual luminosity are the same in that scale, then this and this cancels, and you get 5/5, which is 10 to the power 1. So that means that a star that is 10 parsecs away its apparent luminosity on that scale and its absolute luminosity on that scale will be the same. So if the apparent luminosity is, let's say, 6, and the absolute luminosity is a 6, then that star is 10 parsecs away. So remember, for the apparent luminosity scale, any star that's dimmer than a 2, you would probably need a telescope to view that star at night, especially from LA. If it's a 2, a 3, if the apparent luminosity is a 2, 3, a 4, a 5, any of those, you need a telescope. But if you go to maybe a desert place, you would be able to see it without a telescope. If the apparent luminosity is anything beyond 6 or more, even if you go to a desert, you won't be able to see it, you see? So the more positive the apparent luminosity, the dimmer that star appears. So this star is actually pretty dim looking star. How about its absolute brightness? It's a little bit dimmer than the sun. The sun is apparent luminosity is almost a 5, 4.8 something, so it's almost a 5. So I can say this star is dimmer than the sun a little bit, and it's very hard to see. You need a telescope to see it. And so how far away is it from us? 10 parsecs away, you see? But how about a star like this? So I'm giving you the whole idea of how the equation works. How about a star like this? If its apparent luminosity is a 1 and its absolute luminosity is a 1. This star is also 10 parsecs away. I say, how can the two be 10 parsecs away? Well, think about it. If it's 1, if the absolute luminosity is 1, that's quite brighter than the sun. The sun is a 5, and that star is a 1. Remember, for every 5-fold difference, if the star was a 0, it would be 100 times brighter than the sun. So this star is almost 100 times brighter, not quite. And its apparent luminosity is a 1, which means it looks pretty bright in the sky. You don't need a telescope to see it. So it's a brighter star, and it's closer to you. Sorry. It's a brighter star. So in other words, if this is the Earth, both of these stars would be equidistant. They would both be 10 parsecs away. 10 parsecs and 10 parsecs. So imagine this star that's m equals 1. So it's very bright. And the apparent luminosity is 1. That means you can see it at night without needing a telescope. Very bright looking star. It's bright looking and it is bright, you see. Now this star, little m is 6, so you need a telescope to see it. And its brightness is 6, which is, it's a little dimmer than the sun, you see. So they both be 10 parsecs. Well, that makes sense, because since this guy is a brighter star, it could be still 10 parsecs away from you, but it would still appear brighter because it is brighter. And then here, this guy would appear dimmer because it is dimmer, you see? So you could that makes sense. But now, how about if you have a star that was the little m was a 1, but the big M was a 6. Now let's switch things up. What would we expect? Would that star be more than 10 parsecs or less than 10 parsecs away? So that star is dim. You see, this is the absolute luminosity. That star is dim, so it's kind of like this star, dim, but the apparent luminosity is 1. Oh, that means it appears very bright in the sky. Okay, just from that argument, we would expect that guy to be very close to us. M little 1, and then big M 6. And the equation should bear that out. So you should have 10 to the m minus m, right? Little m minus m. So 1 minus 6 plus 5 over 5. Oh, what does that give you? That actually gives you 1 minus 6 cancels is, no, sorry, 1 minus 6 gives you negative 5. Plus 5 is 0. Oh, it's 10 to the 0, which is 1. Oh, so it's 1 parsec away. It worked out nice. So that means that star is like 1/10 the distance of this. You see? So it's like this. Very close. Right there. That would be a star that is little m1, but big M6. So it's dim, but it appears very bright. You see? So I want you to always, whenever you have formulas, make sense of that formula, understand it and its implications and how it works. Not just be able to learn how to use it, you see. Then if you have the other way around, what if its M is 6, the apparent luminosity, but the absolute luminosity 1? Oh man, this is a very bright star, almost 100 times brighter than our sun, but you need a telescope to see it. 6 is you need a telescope. So that means we would expect it to be farther. So then how would the equation bear that out? 10 to the, now it's 6 minus 1 plus 5 over 5. Right? Oh, which kind of comes out nicely because that becomes, hold on, 6 minus 1, that's a 4. Oh, okay, so that's a 4. Plus 5 is a 9. So 10 to the power 9 over 5. So it's not that perfect. That's going to be almost 100. So hold on, let's see. I'll do it on my calculator. 10 to the power. And since 9 over 5 is 1.8, I can just immediately do 10 to the power 1.8 on the calculator. That's 63 parsecs away. Oh, so it wouldn't even fit on my chart here. That star would be out of this, so very far away. So you see how the equation bears that out, and logic also tells you that, you see. So let's go to stop sharing. Okay, so now let's go back to this. Okay, so then now we know the meaning of that equation, the Hyades cluster. I think this is where we were at. So now we know what to do over there, right? Take 5 pictures and then go over here, start the assignment here. Let's see here. So start. Following the instructions on the Hyades cluster, exercise above to plot the photometric data of stars in the Hyades cluster and determine the distance modulus for the Hyades cluster. So enter the distance modulus m minus m. So then how are we going to do that? M minus m. Total distance to the Hyades cluster. Absolute luminosity. Let's see here. This is the apparent magnitude, and then this is the color index. The HR diagram for the Pleiades star cluster is shown as is a standard HR diagram. So basically, this is the one after you fill out, essentially what this is saying is that after you fill out this one here, after you fill out this one, here, it should look like this thing here, it should look like this one. It should look like this on the left with the color index and then the apparent magnitude on the left. So when we're plotting star clusters, we're plotting how apparently bright the stars are, the individual stars of the cluster, you see. And then on the right side is an HR diagram, a typical HR diagram of stars' actual brightness, absolute magnitude, you see. So then if we go like this, overlap them, let's see here. Drag the Pleiades HR plot over the standard plot and move it around until you find where its red maze sequence curve matches up best with the blue maze sequence curve of the standard plot. Release the mouse to drop the plot. Now you can find the distance modulus for the Pleiades clusters. Choose any line of apparent magnitude on your plot and follow it across until you see where it hits the absolute magnitude axis on the right side of the standard plot. Subtract the absolute magnitude from the apparent magnitude to find the distance modulus. Beautiful, beautiful. So this one is the plot. Essentially, this is the plot that you would have made up here when you did this, you see. And then it's saying they've already done it there. Then you just drag this here, and then you kind of match this here, you see. You don't want to put it there because it doesn't match well, you see. So you want to go like this, match it with the plot right there, you see. Yeah, this one, you don't want to do like this because the bottom ones don't match. The bottom ones are the ones that have to match. Let's see here. Right there. See the bottom one, because the bottom stars of the HR diagram, those are the ones that, let's see here. Oh, but we should, there you go. Yeah, right there. I think we should be able to match their color. In other words, I shouldn't go past this or to the left. I should match the horizontal because the BV index on this one should match with the BV index of that. So I can't go more to the right or more to the left. I can only like go like this, and I can go up and down. You see, like this. No, this is too far up. This one like this. Now let me release it. I think that should be right there. And now let's zoom in. Not too bad. When you zoom in, it's like, yeah, there you go. Okay, that's good. So you see, basically what we want to match is on the left side, you see the apparent magnitude is 12. Let's say right there, 12. Right there is a good match, I believe, right there. So the 12 on the left matches with the 6 on the right. So in other words, a star on on the Hyades cluster, a star that has an apparent magnitude of 12 will be a star that's absolute magnitude of a 6. So the big M is 6, and the little m is the 12 on the left. So the left side is the little m, and the right side is the big M. You see? So then the 12 matches with the 6, or the 13 matches with a 7. You see? 14 matches with an 8. 15 matches with a 9. So that seems like that's the best match right there. Okay, so then you take a picture of that right there. Oh, yeah, I should match the horizontal scale like this. Yeah, right there. No, hold on. It should go up. Something like that. Right there. This isn't easy to do. Technical. Yeah, okay. So it seems like 12 matches with a 6, but it's not quite that good of a match. So I would say apparent visual magnitude 12 matches with a 6. But what you could do, take a picture of this and then assume your little m is a 12 and your big M is a 6. Then put in the values here for the modulus, m minus m, and the total distance to the Hyades cluster, what would that be? If it doesn't accept your answer, then you have one more try. Then you would have to go back down here, play with this again a little bit, and you might have to guess halfway between 12 and 11, you know? So it might not be an exact whole number. And then go back up here, change your guess, and then put in the distance, and then your second try, see if it works. It might take 2 tries, and if you don't get it by then, that's fine. Just put whichever one, just put the two, just put the whichever one was your second one in the report and the picture that you took. If you don't get it, but okay, so let's see now. Start another one. Was that? Use the Pleiades cluster above to determine the distance modulus and the distance to the Pleiades cluster. Oh wait, this is the Pleiades. This is the Hyades from all of the instruction. Plot the photometric data stars in the Hyades cluster and determine the modulus. This is the magnitude for BV index. Oh, wait. So this one here is for the Hyades cluster. And this one is actually for the Pleiades cluster. Oh, actually, these are two different star clusters. So this one is actually this one. The picture here that you did goes with this one, M minus M and D, right? That one goes with this one. And then the picture here, this one is based off this picture. Let's see here. Oh, it seems like this one, you need to finish all of this before this unlocks something. Because the thing is, we need to, once you're done with this, let's see here. The Hyades cluster exercise allows you to find the apparent absolute visual magnitude and distance to the modulus for the Hyades cluster. Look first. So basically, oh, okay. Here's what's going to happen. Once you place all of these here, it will create something like this, equivalent to the Pleiades cluster. But then after that, it needs to, I believe, once you're done, then it will unlock the next one where you can take this and drag it over to another chart that looks like this. You see? I wonder if you could drag this. I don't think this is draggable right now, you see? So I believe once you are done with all the stars here, it will then take you to another page here. Since I wasn't done, I didn't see that. It will take you to another page where you can drag this over to the HR diagram. Then you could do the same process that you would do for the bottom one, you know. So I showed you the one for the Pleiades cluster. And then you're going to do, first you're going to create this guy here for the Hyades. And then you're going to place this. They'll probably unlock an HR here, and then you'll place this there. So we could kind of look up online and say Hyades cluster. It's a famous star cluster. Oh, beautiful. This is the Hyades cluster. And it's in the constellation Taurus. You see here? This is the constellation here, Taurus the bull. And that's the Hyades cluster right there. It's in that area. You see here? This is the Hyades cluster right here. Oh, there's Aldebaran right there. We mentioned Aldebaran a while ago. Aldebaran right there. This is the Hyades cluster right here. And then that's the Pleiades in the sky. Pleiades is even brighter looking, and it's more densely packed with stars. So star clusters are these dense conglomerations of stars. The Pleiades more densely packed. So both of these, it seems like, are in this constellation Taurus. The star clusters of Taurus, the Hyades and the Pleiades, right? They're famous in history. So in Greek mythologies, the Hyades were the 5 daughters of Atlas and half sisters to Pleiades. So there's always this beautiful Greek mythology connected to these. It's the 5 daughters of Atlas and half sisters to Pleiades. After their death of their brother Hyades, the weeping sisters were. So it should give you a little idea of the distance to the Hyades here. Distance 47 parsecs away, you see. So that's kind of like cheating, but hey, I'm cheating right here. So we would expect the Hyades to be around 47 parsecs. That's your calculations. And then for the Pleiades, what would that be? So the Pleiades, also known as the Seven Sisters and the Messier 45, is an open star cluster containing middle-aged hot B-type stars. You see? So these are called the Seven Sisters. And they're both in the Taurus constellation. Okay? And the distance to this guy is 136 parsecs away. So even though in the sky, their position is close in the sky, that doesn't mean their distance to us is the same. One could be very far away, one could be very close. Their position in the sky has nothing to do with their distance from us. So the Pleiades is farther away, 136 parsecs away, whereas the other one, the Hyades, is 40-something, 47 parsecs away, right? Nice. Okay, so, oops. Okay, so let's go on to the next one. Leaving the main sequence. The age of a cluster can be estimated by observing where its curve turns off from the main sequence on the standard HR diagram. Like you see, when we Googled this, did you notice that they all gave a certain age to the cluster? Like right here, they said, where was the other one? I think one of them already said the age. Yes, the estimated age, 625 million million years old. So in other words, we already know that the Hyades cluster formed 625 million years ago, roughly. That's what its age is. So that's what we're going to learn next. How do we age these clusters? When did this cluster form? 625 million years ago. Imagine that. That's actually a very young star cluster. Our sun formed almost 5 billion years ago. So this one is a very, very new star cluster, the Hyades star cluster, very new. So, but the age of a cluster can be estimated by observing where its curve turns off from the main sequence on the standard HR diagram. For obvious reasons, this point is called the turnoff point. The stars at the turnoff point are just now exhausting their core hydrogen fuel, and therefore their main sequence lifetime is a good estimate of the age of the clusters. You see? So notice that the lower branch, they're still living. The low mass stars take much longer to die. So they're still living stars. The high mass stars have already begun to die. They're moving off the main sequence and they're branching off. That's called the giant branch. So that star cluster, we can know its age if we know the turnoff point. Again, once we click on it, we probably see a better image of it. You see the turnoff point. But on this one, the better image is not going to show us that much more detail. See the turnoff point right here? If we know the properties of that star and where it is, we can approximate the age of that star cluster, because that star is about to start dying right now. You see? It's moving off the main sequence. So the spectral type of the stars at the turnoff point is determined from the standard HR diagram. Complex theoretical stellar models are used to estimate the main sequence lifetimes for each spectral type. So here it says the turnoff point exercise. This is an HR diagram in which the plot for a globular cluster has been fit to the main sequence. Position the mouse pointer over the graph, left click and hold to activate the crosshairs, and then use them to read off the color index of the turnoff point from the bottom axis of the diagram. Wow. Oh, okay. So we could go at any point and then crosshairs, you see the color index. So where's the turnoff point for this one? It's kind of hard to tell, huh? Is this the turnoff point? So this is a globular cluster. That means those are usually older, the globular clusters. So position the mouse pointer over the graph, left click and hold to activate the crosshairs, and then use them to read off the color index of the turnoff point from the bottom axis of the diagram. So if you think that this is the turnoff point, you know what? I think this is the, let's see here. I believe somewhere here. So the BV index would be what? 0.4, 0.2, 0.3, 0.4. It looks like around 0.4. Then what else can we do here? Start. Based on the HR diagram above, which cluster? Okay. So this exercise comes first. The turnoff point. Let's see here. Yeah. Oh, okay. So they showed you here the different star clusters, the M67, the M11, NGC, Hyades. These are all different Pleiades. Notice that from that chart, the Pleiades looks younger. That means its turn-off point is higher, right? Based on the HR diagram above, which cluster contains the largest percentage of high-mass main sequence stars? Which cluster do you suppose is the oldest, right? So the ones that, like, for example, Pleiades, most of its young stars are still living. The heavy bright stars are still living. So Pleiades would still be younger than Hyades. So let's see here. Hyades, the age was 625 million years. Let's look at Pleiades. Pleiades cluster age. It should be younger than 625 million years. There you have it. You see? So I could just guess from basically looking at that chart, because it has a higher turn-off point. That means the star that is dying, just beginning to die in the Pleiades cluster, is higher up the main sequence, right? Because remember, brighter and hotter stars live shorter lives. So that means this must be a younger star cluster that it still has a brighter star still living and just beginning to die now. So the Pleiades cluster is 100 million years old. Very, very young star cluster. Of course, for our lives, that, you know, compared to our lives, that's crazy old. So now, okay, so then you, for this one, you just actually just answer and then take a picture of your result. And then take a picture so that the graph actually shows, you know. So when you answer this, like this, kind of fit this picture so that you could show you're basing your answers based on this top picture, you see. And then you go to this exercise. This one might require two pictures. So one for just the graph, just this graph, and then one for the answers, so that you can show how you're basing these answers off. Okay, then you go over here, age of the M3 cluster exercise. This is the M3 right here. It's an M3 globular cluster. Start. Use the age of the M3 cluster tool above to determine the BV color index of the main sequence turnoff point for M3. Use the table above in the BV color index. What is the approximate age of M3? Okay, so then you got here, use the age of the M3 cluster tool to determine the BV color index of the main sequence turnoff point. So if, let's say, I thought that the main sequence was the 0.4 right there. Then I take a picture of that. Then I would come here and I would put the BV color index is 0.4. And then you would see here, if the BV index of the turnoff point star is 0.4, then you look at this chart, then what would its main sequence age be? Let's see here, 0.4, where does the BV of 0.4 go? 0.4. 0.4 like goes here, you see, almost basically right there. So that means the age of the star, the age of the cluster must be the same as the age of that turnoff point star. That means that star cluster was born roughly around the same age as that star was born, you see, because we know that that star is about to die. And so if that star is 3,000 million years old, then that means the cluster must be that old. What does 3,000 million years old mean? See, that's 3,000 times 10 to the 6th. So that means 3,000 times 10 to the 6th, that's 3 times 10 to the 9th. That means that star is 3 billion years old, 3 billion years old. And therefore, the age of the M3 cluster, is it 3 billion years old? It could be. So then you would put that here. Well, they have it in million years. So you would put 3,000 million years and then submit your answer. So I'm already giving you the answer. I think that's what it is. But if it doesn't work, then you kind of can change it. Let's see, what is the M3? M3 cluster. Estimated age. No, it's 11.39 billion years old. So I was off on my estimation. 11.39 billion years. Giga is a billion. So if you think that it's 3,000 million years old, that would be 3 billion years. Wait, 3,000 million, yeah, 3 billion. Wait, I was way off. Globular cluster Messier 3, M3. Yeah, way off, right? From that answer. That's interesting. Let me just try here, 3,000 million years. Partially correct? Oh, but it doesn't tell you what it is. Try another version. Yeah. So on this app, it doesn't really say how far off you are, you know, but thankfully we've got Google that helps us, you see. So that means we need to up our age. Well, to up our age, that means what? You see, Google can help us to see at least how we are wrong. Maybe we're reading this chart wrong. Maybe the turnoff point is, I believe the turnoff point could be, you see here, according to this chart, the turnoff point is like here. There's a horizontal branch here. These are stars that are dying, or yeah, there might be stars that are going off and then coming back. So they're dying. So the turnoff point is somewhere there. But when it's cluttered, you can't really tell which one is the turnoff point. Maybe this one. Let's see here, the point. Maybe this one is the turnoff point. This one is hard to guess. Okay, how about right here? That would be 0.55. 0.55 would be the BV index. And then if you go to 0.55, the BV index, so we're looking at, see, we need to go towards 10,000 million years. So in other words, yes, I was true that the turnoff point is somewhere below, somewhere down here, you see. So basically we're trying to say which star is still living here, hasn't moved off the main sequence. The rest are starting to die. So see, these are all living stars. Somewhere here probably. And then based on this chart, based on the BV index of that, then you guess a number between, let's say you might not even be exactly 0.63, you might be 0.65, you're guessing. So you might guess a year between this and this, you know. And so there's a little bit of guessing on what number to put here and see if it accepts that. Hopefully we'll accept as we get closer to this age, it should accept that answer. But, you know, but base it off of your chart. In other words, don't just put this answer and don't base it on your result here. That's when Google is dangerous. Don't just use Google just to get the answer, because then you're not basing it off your reading here. So you have to take a picture here of what your reading is, and then base your BV index based on your crosshairs, then go in here, decide where you are on that chart, on the BV index chart, and then guess a number for the main sequence age between the numbers given. So if your number was like 0.60, then you will be slightly younger than 10,000. Yeah, right? And then you can try the answer and see what your answer comes out. Okay, I think that's it for that part. Okay, then you get here, did we do the leaving the main sequence? Oh, I think we already did that. Let's see. Oh, okay, so we did that. Wait, did I? Distance modulus, leaving the main sequence. The turnoff point on the HR diagram. Oh, okay, hold on. How old? Oh, okay. You know what? For some reason, it keeps skipping the first page of these. The turnoff point on an HR diagram indicates which stars are just leaving the main sequence. Oh, okay. So we actually went past this. It talks about what the turnoff point is, and the supernova stars that go supernova on the way top, the red giant branch, and the main sequence. Stellar evolution. Here's an interactive HR diagram that will allow you to explore and the HR diagram. Oh, okay. Oh, yeah. But this one, I don't think is an actual exercise that you have to do. Let's see here. Go like this. Go. It just basically says the older the star is, you see how the young stars start to die, the bright stars start to die earlier. You see? Then so the 20 means 20 times heavier than the sun. And 9 means 9 times heavier than the sun. So the 20 mass star starts to die way earlier than the 9, and then the 5, and then the 3. So you see, in about 2 million years, the 20 mass star starts to die already. 2 million. Then 5 million years, the 9 solar mass starts to die. Once it does this, that means the 9 solar mass star has already died. So the 9 solar mass star died in 33 million years. Now the 5 solar mass star, oh, right there. 5 solar mass star died. It took 97 million years for it to die. Right? So what is our life? Our life is 60 years, 80 years, 90 years. It means nothing. Stars laugh at us. They live, this 5 solar mass star will live 97 million years. And our sun will live almost 10 billion years. And then the 3 solar mass stars starting to die. You see? Stellar evolution. Oh, here's an exercise. This one, you just take a picture of it, just your answers. I don't think there's any math on this. Yeah, so this one, there is no math. You just take pictures of your results. Then that takes you to the turnoff point, which we did. The age of the M3 cluster, which we just did. And I think that ends it. Okay, I think that ends it. Let's see. Summary. Yeah, so that it gives you a summary of what we talked about. So I just want to make a general point is that sometimes when I'm explaining things, I'm trying to also explain it as if some of you have not had astronomy lecture, or maybe you have had, but you've forgotten the material, or maybe you have had astronomy lecture, but you never covered the material. So I'm talking about HR diagram and the lifetimes of stars and the BV index. Some of that stuff you would have learned when you took the lecture, but you might not have covered it or you might have forgotten it. So the two kind of go together, the lecture and the lab. But you could also, even if you've forgotten it or you've never taken it, you could always Google things and use Google and YouTube videos as your friends. You know, you could always go YouTube something, see a video of it. You could Google things. For example, if you're interested, if something piqued your interest, you could go and just go to YouTube and click some kind of, let's say, Hyades Cluster. So something interested you. Let's say the age of the clusters, you know, and then you could watch this. How do we measure the age of a cluster? So on any of these topics that we're covering.
Hi there, welcome back to the.
On any of these topics that we're covering, if the video itself and your previous experience astronomy lecture is not enough, you could always go and view videos and then put that in your discussions, like maybe even put some video links of things that help you or Google sites that help you or whatever websites that help you or crash course. You see, this crash course is really beautiful. Crash course videos.
In the last episode, I talked about stars that are orbiting one another. When it's two stars, it's called a binary.
You see what I mean? So try to use those resources that the web is just so full of, and then use them as like a guide, not just to do the lab, but to learn the material of the lab. You know, to refresh your memory of what you learned in the lecture, or maybe if you haven't had the lecture, to learn the material. So like, for example, this video is on the how to age the star cluster, you know.
Hi there, welcome back to the Cosmic Classroom. We'll now talk about star clusters. Hi. So there are different kinds of clusters of stars. Some clusters are open clusters, cluster that's relatively young. You see a lot of gas still around the stars still forming. It's stars that have formed recently, actually. They're not still forming, but that have formed very recently. You still see the gas. So this is a pretty young cluster. And there are older clusters, like globular clusters that have.
Remember I said the globular clusters, the M3 is the older ones.
And, you know, have redder, so the stars are redder. So just by looking at those two figures, we already have an idea that the Pleiades is younger because it's bluer, right? Than the globular cluster, which has redder stars. But how can we really put an age to those stars? Is what's the subject of this little video here. Now, you need to, in order to understand that, you need to go back and recall what an HR diagram is. So an HR diagram plots surface temperature and luminosity. So in the x-axis, we have surface temperature, and hot is to the left, cold to the right. So those are hot stars, cold stars, and luminosity increases as you go up. So right here, those are the blue hot stars, and right here we have the red low luminosity stars. So if we look at the stars in the Pleiades, we can go to each star. You see a little triangle there? We can go to each star and measure its luminosity and measure its temperature. It's pretty handy to do that with clusters because we can measure the relative luminosity of stars. We don't need to know the absolute luminosity because they are all at the same distance from us. So all that really matters is whether this one is brighter or fainter than this one. It doesn't really matter, you know, exactly how many joules are being emitted per second by this star or by that star, okay? So we can do that for different stars. And we can do that for all the stars that we see in the Pleiades. And we see stars all over here in the main sequence. But we don't see stars that are hotter than B stars. There is no star hotter than a B star. There are no star as hot as an O star. And in fact, the stars that are between, there's late A star, early A stars right here, they are leaving the main sequence. So what this plot tells us is that all of the stars, O and B stars, they are not in the main sequence anymore. They have already died, okay? If they have already died, and we cannot find any stars with less than around 100 million years of life expectancy, we know that this cluster has to be more than 100 million years old. It has to have had time to form all the stars and to let them die, okay? As this cluster gets older and older, these stars are gonna die, so they're gonna move away from here. And then the colder stars are gonna die and die and die. So the fact that we don't see bright O and B stars tells us that this cluster has had time for all the O and B stars that were.
Okay, so you can kind of see how they go through some of the similar explanations that I went through, but then you can get a different perspective, and you can definitely link up those links in your discussions, help each other out. And as a class, we will really, really learn a lot. The more you participate in the discussions, and I try my best to give you the explanations, but you have to also kind of put in the work, to learn, to watch the videos, to do external searches. These are great websites. The crash courses I really recommend, or any other videos that you find on YouTube. Really. Okay, guys. See you later. Bye-bye.